Hello everybody, I'm your host Hal Curtis and I'd like to welcome you to The Space Industry by SatSearch, where we share stories about the companies taking us into orbit. In this podcast, we delve into the opinions and expertise of the people behind the commercial space organizations of today who could become the household names of tomorrow. Before we get started with the episode, remember you can find out more information about the suppliers, products and innovations that are mentioned in this discussion on the global marketplace for space at satsearch.com. Hello and welcome to today's episode. I'm joined today by Fredrik Bruhn from Unibap, a public corporation headquartered in Sweden that is using AI and digitalization to improve industrial technologies, both in space and on Earth. Fredrik is also an adjunct professor in robotics and avionics at Mälardalen University in Sweden, and Unibap is a SatSearch member company. In the space industry, Unibap develops advanced payload processing solutions that use AI and edge computing capabilities. And today we're going to discuss a little bit about the use of AI and machine learning in Earth observation applications, and maybe touch on some other applications as well. So firstly, Fredrik, I'd like to welcome you to the podcast and ask if there's anything you'd like to add to that introduction about yourself or about Unibap.
Thank you very much for being invited, Hyvel, for that nice introduction. I think you summarized it quite well. So I think we can continue with the show.
Okay, excellent. First up, the overall use of AI and machine learning applications in terrestrial and space-based areas. So I wonder what you thought were the biggest differences for designers of terrestrial and space-based AI and machine learning applications.
So that's a very interesting question. And actually, we're probably going to discuss that in more detail. But the whole purpose of our development and coming out with Space Cloud as an infrastructure for the space market is to allow the same AI tools to be used on ground and in space. So if you look at the applications that are being developed right now for spaceflight later this year with Space Cloud, it's using the same tools and the same training mechanisms that you do on ground. So we have actually been able to demonstrate that we can port very advanced Earth-based AI algorithms in a matter of hours to Space Cloud. And then we are able later this year to orchestrate them in space with the same kind of orchestration tools that you have on ground. So I would say that the differences going from Earth to space is rapidly becoming less important, and it's becoming less of a hurdle. It's very easy now to port and develop and orchestrate different algorithms in space. So the boundaries are being blurred out.
Right, interesting. I think we're seeing that in a few areas of technology. So it's good to know that in this processing application that the boundaries are blurring there as well. So, but obviously this space does provide the unique environment in a set of unique challenges, perhaps for different applications. So on maybe in the technical side, from the engineer's perspective, what do you think are the biggest challenges for integrating AI and machine learning?
So that's a different story. Obviously, it's a very different environment, as you mentioned, in space. And you have a global coverage, which you don't have with terrestrial systems. But in terms of integrating this, it's not that difficult, actually. We have packaged our infrastructure into small CubeSat-compatible computer packages that you inject into your spacecraft, much similar to an OBC. So from a user perspective, it looks exactly like an Earth-based terrestrial server. And from an integrator standpoint, it looks like any OBC. So you're integrating it with the same tools, same electronics designs and design rules and things like that. So it's interesting to see that with the proper packaging, it's really like going down, buying a desktop computer, installing it, and off you go. It's almost that simple.
So a sort of modular approach has been built in from the very start.
That is correct. And I think that's very important because the whole purpose here is that we are trying to create a cloud computing experience in space. And we want to eliminate as many differences as we can from a user perspective and an integrator perspective. So we are trying to keep as many things as similar to what you're used to as possible. And I would say that from the integration projects we have had so far, we've been quite successful because the feedback back to us is that, wow, this was really easy, both to develop applications for as well as integrating.
Oh, great. And that's obviously a key technical challenge. Just to talk about an application area, really, in Earth observation, obviously optical cameras are one of the big areas that need to be dealt with. And they face some unique challenges when used on satellites and other spacecraft for different reasons. There are clouds, there are atmospheric effects, and there are various other things that can disrupt signals or cause a lack of image quality that doesn't meet the end user's requirements. Companies are trying to get around this in different ways. There are obviously, you can have multiple cameras, constellations, you can schedule passes at different times. The ground segment is working in different ways, but these atmospheric effects are still there. How can AI be used in the context, or can AI be used in this context to help overcome some of these limits?
It absolutely can, not just AI per se, but smart algorithms. So if you have a true cloud computing experience on your spacecraft, or you have inter-satellite communication between them, so you can create ad hoc networks. That means if you have that kind of capability, you can start to generate actionable information on board your spacecraft, and that actionable information can be shared within the constellation as well as being shared with the ground stations. And then you can start to reason in that data set, and you can start to reason about a good mission profile, which means that you can start now to autonomously task different satellites for different purposes. You can even task different ground stations for different prioritizations and things like that. When you enable the possibility of reasoning within your system, you can create some very elaborate and autonomous mission concepts as well. So if you have atmospheric effects, you can obviously, if you have a particular customer requirement, you can task your SAR radar satellite or your optical satellite or a LiDAR satellite to cooperate over a certain area and then build up the scenery from different points. And you can even start to think about having autonomous data fusion in space as well. So all the tools that you would deploy on ground are now becoming available for you as a mission designer in space as well.
Interesting. So it's really a set of more advanced, payload processing technologies that are now available on orbit. And compared to current solutions, I mean, you've probably touched on most of the advantages there, but is there anything else that these systems are offering that is novel and that could be of, major benefit to mission designers in future missions compared to what is live today?
So what I think is that if you go back to the fact that we stated that we're trying to make it as similar as possible to what you have on ground.
Yeah.
The fact that we have been able to take the entire NV IDL suite from L3 Harris, and we were able to port that into Space Cloud and also port an advanced application in about 4 or 5 hours. That's a tremendous step, because if you are looking at ground-based geospatial intelligence, it's often using third-party libraries. NV is just one of those libraries that is commonly used. And now you can harness the entire power of that software suite in Space Cloud in space. So if you have an application that makes use of NV on ground, you have that infrastructure also in space. So in certain cases, you can actually take an algorithm and just compile it and run it in space without any changes. And then you may want to do some optimizations, and then it takes a little bit more time. But in many cases, we have been able to show over the last months that you can take an existing algorithm running on your laptop or on your x86 server on ground and directly deploy it onto Space Cloud without even a line of code change.
Part of what you're doing is about building an infrastructure that enables mission designers and operators to run aspects of code or whole processing systems that are individual to them. And my next question was about this, heterogeneous compute solution. If that capability is brought into satellite operators, does it convey them certain hardware and software advantages? Could you maybe touch on a few of those?
Absolutely. And I think, again, with the analogy, what it looks like on ground, if we go back to a normal cluster or compute solution on ground, you typically have the ability to ask for additional CPU resources. You can ask for extra GPU resources. Maybe your data center is offering FPGAs to you. Maybe you have other neural network accelerators included as well. So if you go to an Amazon Web Server data center or a Microsoft or Google, you have a heterogeneous architecture in all of them. So what we are offering now is a heterogeneous architecture in space. Obviously, you could say that it's a data center in miniature. We don't carry a full-blown data hall with us, but It's a heterogeneous architecture that allows you as a application developer to make use of the best available hardware resources when you need it. So your application can request from the orchestration layer to have one or two or three or four CPUs. You can request to have access to a GPU. You can request to have access to vision processing neural network accelerators, or you can ask to have access to the FPGA. Obviously, the FPGA route is a little bit more tricky, as most of our listeners know, but you do have all those resources included. So it's very similar to what you would find at Amazon, for instance, with Lambda services and things like that.
Now, there's also quite a big movement in the industry towards the integration of cloud for data downlink and distribution, particularly in Earth observation. And how do you think that cloud-based solutions and architecture go along with AI onboard satellites, in Earth observation missions?
They really go hand in hand, I would like to say, because it's not either or, it's actually a combination. And we announced a few months ago a partnership with Amazon Web Services that we are going to deploy some of their edge services into Space Cloud. And the whole purpose here is to optimize that you can think about a system of systems. You can have part of your compute solution on ground. You can have part of it close to the antenna farms, for instance, and you can have part of your compute problem in space. So you can have algorithms that are doing cloud detection, cloud removal directly in your spacecraft. You can have actionable information being processed in the spacecraft, and then you load that to ground and you start to reason about what kind of raw data do I want to download? Do I want to download all of the data, or do I just want to download certain bands from a hyperspectral sensor, for instance? So you can start to filter and analyze the data. So this is the perfect analog, I would say, to edge computing in industrial IoT, where you spread out sensors throughout your factory, you start to reason in the edge, and you get a picture about what the big system really should do. And now we can offer the same kind of services and same kind of thinking also to spacecraft and space solutions.
There is a bit of a difference, though, isn't there? Because this, like we've talked about, the space environment is so inaccessible. When something is launched, it's launched. At the moment, anyway, at the moment. So there's going to be space hardware and code flying on different missions. And you've mentioned how different aspects of the overall system will be based in different areas. How do you think the systems can be updated and maintained from the ground, particularly when you need to retrain existing models or orchestrate applications that weren't part of the original mission design?
That's a very good question. And part of the answer is that if you have an onboard orchestration layer like we do, you can very easily deploy new containers into your spacecraft and orchestrate them. And if you're familiar with the high performance community on ground, you would know that you can upload what's called partial containers. You can have containers that are riding on top of other containers. So it's fairly easy to upload data that are a delta of what you already have. So if you're uploading a new model, you don't need to upload a completely new container with everything you uploaded before. You can upload a container with only the model, and that can still be called from the original container. So doing partial deployments, that's what it's called. It's fairly trivial if you have orchestration layer that is compatible with the ground-based tools. So that's one set of it. The other set of it is to use other technologies for training. So one of those training sets would be to, for instance, use solid-state drive computing. I don't know if you're familiar with that, but there is a new moment on ground in high-performance computing to use AI accelerators inside SSD drives, so that the training data never needs to leave the drive. So the training data can be used to train directly in your solid-state drives. So that's also a trick you can deploy on heterogeneous architecture to minimize the power consumption.
Right, so it seems there are really some new tools and processes for orchestrating AI applications in orbit that haven't been used in this space context before.
That's true. They haven't been used in space context, but they are used every day on ground. And that's the whole idea. Use whatever we have on ground and that all the youngsters are educated at the universities. Don't reinvent the wheel.
Absolutely. And with these new tools and these new capabilities, do you think there are, a number of emerging applications that maybe nobody could have thought were possible a few years ago?
Absolutely. I've seen some pretty wild ideas out there at various conferences. I saw last year at a conference a company who are planning to build server infrastructure in space, basically launching satellites with the only purpose of providing massive compute capabilities and then offering intra-satellite communication links to other satellites that don't carry the same capability. So you can choose to send your raw data down to ground, or you can send your raw data to one of these flying fortresses or flying data centers and process your data and get the result back from those flying data centers, for instance. And I haven't seen that in space industry before, but ideas like that started to pop up maybe a year ago.
Right, fascinating. I mean, does it get more environmentally friendly as a data center than being based in orbit? Possibly not. Now, it's evident that there are advantages that you've mentioned with both AI and cloud-based solutions, and you've discussed how they are integrated together and how they should work well together. Are there any other unique advantages that maybe combining using AI and cloud on satellite missions could bring?
Other features that should be of interest is that if you have a cloud computing infrastructure, you have tools like the S3 database API from Amazon, for instance, which is now a widely used standard. So you can start to format your data according to industrial standards, and then you can interact between your spacecraft and ground using those industrial standards. So your data pipelines becomes much easier as well. There are many other aspects of this as well that are interesting. AI, as the listeners are familiar with, is not a one solution to rule them all. AI is really only a mechanism to sort through massive amounts of data in a novel way. So you need to actually have all the other pieces as well to create a system.
Building on that, I think one of the areas in the space sector that is generating this massive amounts of data where AI will certainly be of use is the autonomous satellite constellations. The size of some of them that are proposed are enormous, and as the sensors are growing and their capabilities and the different cameras and whatever else they're using are growing, the collection of data is enormous. So what do you think is needed to get into a position to realize a system where AI is used to, improve the operations of autonomous satellite constellations?
Well, I don't think that much else is needed. I think all the bits and pieces are out there. So I think it's more or less mainly that operators want to do it, and they can probably do that. We've had a number of customer requests already, and we know that there are being prototypes developed on our engineering hardware for similar missions. So autonomous mission operations is actively deployed in some cases already, and it's being heavily invested in already. And we do know that our tool suite of Space Cloud can enable that.
On Unibap side, then, maybe you could just tell us a little bit about how mature the technology is.
So in terms of the technology, we have flown quite many systems in terms of the compute part since 2016. We have developed what we call the IX5 100, which is a complete cloud computing platform. And that's being flown by NASA this year on the hyperspectral thermal imaging mission. And we just recently, a few weeks ago, announced that we are going to fly the full-fledged space cloud orchestration layer together with the European deorbit company. And that will happen in the second quarter of this year. So it's aligning quite nice, and we should be able to reach TRL 9 at early next year.
Oh, fantastic! Well, best of luck with those missions and completing everything else needed to get to that level. My next question was going to be about how the systems that you have or that similar companies are developing can be used in current mission designs. I think you've pretty much covered that. So I was wondering perhaps what you saw was the next step in terms of what's available for satellite operators and engineers.
That's a very interesting question as well. And we have announced that we are working on something that we call the IX10. And obviously we have the IX5 product. And so IX10 would be the next logical step. So we are pushing out the performance in about 100 times more in the new system. We are increasing the data bandwidth, going up from 6 gigabits per second in the current generation to a maximum of about 27 gigabits per second on the new generation. And we are already laying out a roadmap for the coming 15 years with new releases of Space Cloud in terms of both hardware and software. So we are working very actively together with the European Space Agency and the Swedish Space Agency on this roadmap. But we are also working very closely with our customers to do tailorization, because as you know, there are rarely the case in space where several different spacecraft use the same kind of interfaces. In space, we really love to switch out connectors and change interface specifications. So we are modifying the I/O boards of our products quite often to adapt to different interfaces and to different connectors and things like that. But apart from those modifications that you always need to do, most of the rest of the system is a standardized block where we have actually connected a number of these systems online so that you as a customer can log in remotely and test your code, and you can experience this remotely, especially in these COVID times. But also that's a very nice model. So for instance, the NASA integration has been done from Hawaii, and they've been integrating here in Sweden from Hawaii remotely. So that's been a very nice experience. But the other thing is that Space Cloud is also using Docker. So we are hosting our own Docker registry, which means that you can download the SDK and get going on your application development just by downloading the Docker SDK from the registry. And what's interesting is that once you have packaged your application, you can upload that to our Docker registry, and we can automatically push that out onto flight hardware and run your application on real flight hardware, and then send you a report back very quickly stating what performance you received, if you had any compliance issues and things like that. And that also makes the integration process very much easier than what it used to be.
Yeah, it's such an important part of bringing these new technologies to the market. And so it's great you've been able to focus on that and test it in different ways and from around the world. So in that sense, I think what a lot of this always comes down to is the commercial realities of the new products being developed. So on that side of things, I know we've touched on a lot of the capabilities that AI and cloud solutions can bring. Do you have any sense of what the ultimate benefits can be to satellite operators, servicing their customers in terms of saving time, saving money, whatever it is?
It's actually all of those. So the hardware is obviously more complex than if you put a smaller processor into every single experiment. However, the software development for that kind of system will be much more complex. So here you really trade a slightly more complex hardware solution of all the benefits of having almost 0 time software development. In many cases, you can take whatever software you have on ground and fly it. You also trade development costs, because if you really free up, I would say, a lot of engineering hours on software development, your overall mission concept cost goes down. The other thing is that you have now a flexible concept that is easy to upgrade. You can orchestrate different applications. These applications can be isolated the same way you do in a ground server. So you can have 2 or 3 different apps running in parallel. And you can also now start to think about real isolation, where you have military grade data in one container and you have commercial civil data in another container, and you can start to host them on the same vehicle. So you can now begin to really think about the same kind of data-centric cloud offloading that you have on ground, but in space. And this is also something that we are pursuing as well, to get certifications that you have the same level of isolation that you would on a GovNet, for instance, from AVS and similar things. So it really opens up a complete new world, which isn't new. It's the same world that any IT department would work with on ground, but it's now available in space. So you can start to bring in your IT department that usually make sure you have a desktop computer in your satellite company. they can now actively participate in your space programs, and they can support you with intelligent algorithms, and they can do all sorts of things that they are used to do on ground.
Right, so you can use the resources you already have.
Absolutely. And since you can host almost an infinite number of algorithms as long as you have storage capability, you can also now finally get to the point where you have a data-driven business model. You can start to generate data products in space. You can service many different customers over different areas by rapidly orchestrating different applications. And maybe you can also speculate and launch a satellite with only 20% utilization during launch, because you can fill out the other 80% over time in an easy manner as well. And if the regulation approve, you could also isolate the cloud compute part from the rest of the satellite and maybe have users directly uploading their containers into the spacecraft as well. Similar to your cell phone, you choose which kind of apps you download and when you download them for the purpose that is your interest. So maybe the operators don't need in the future to be involved in every uplink, in every data product, etc. Maybe that can be handled more and more by the customers themselves.
Right, interesting. So it's bringing the idea of AI and cloud-based solutions into almost becoming plug-and-play applications. Now, I think there's, as you said, there's a few steps to go there, but this ability to almost access intelligence as a commodity, or to compartmentalize different parts of your system and upload them separately on a timescale that suits you, using the resources that you have on the ground and the things that you already use in terrestrial applications is fascinating. So just as a final question, I think, to put you on the spot a little bit, I wondered if you had a prediction of how far away we are from seeing this occurring, this being a regular facet of a space mission.
Being a regular facet is probably a couple of years down the road. As I mentioned, we have already put out announcements that we are working and collaborating with AVS. And in that announcement, we mentioned that we are doing testing and validation during 2021. We've also told you that NASA is using a version of this on the high-tide mission as well, being launched later this year. The flight hardware is already delivered. We've also told you that together with D-Orbit, we are also launching and verifying the orchestration layer in the second quarter of this year. So we are rapidly ramping up to deploy this now and to demonstrate it and reach TRL 9 next year. So I would think that it's fair to say that you're going to see this in different shapes and forms over the coming 2-3 years. And definitely in 4 years, it will be very widespread.
Great. Well, I think that's a great place to wrap up conversation. I think it would certainly be really interesting for the industry to access computing capabilities in this way and bring the cloud and the ground closer together, bring terrestrial and space applications closer together. And it could bring some really amazing opportunities for Earth observation and for other sectors that many of which you've touched on. So thank you very much for sharing your insights with us today on the industry and Unibap's work, Fredrik.
Thank you very much for being invited, and we're happy to come back at any time.
Yeah, you're very welcome for being here with us today. And to all our listeners out there, I wanted to thank you too for spending time with us. And if you'd like to find out more about Unibap, please head to the global marketplace for space at satsearch.com, and you can use our free request system to get technical details, documentation such as datasheets or CAD models, etc., quotes, introductions to companies, and whatever else you might need for your trade study or procurement purposes. Thank you for listening to this episode of The Space Industry by SatSearch. I hope you enjoyed today's story about one of the companies taking us into orbit. We'll be back soon with more in-depth, behind-the-scenes insights from private space businesses. In the meantime, you can go to satsearch.com for more information on the space industry today, or find us on social media if you have any questions or comments. To stay up to date, please subscribe to our weekly newsletter, and you can also get each podcast on demand on iTunes, Spotify, the Google Play Store, or whichever podcast service you typically use.